Hello students, in this video we'll provide a justification of why a particular second-order differential equation has trigonometric solutions. In this video we'll consider the constant coefficient ODE, y double prime plus y is equal to 0. What we'll do is we will try to find the solution of this ODE by looking at a Taylor approximation or a Taylor series of the solution centered at the origin. So we'll write the solution as its Taylor series. The advantage of writing a solution as a Taylor series is its derivative is very easy to compute. The derivative of this function, the derivative of a0 will be 0, the derivative of a1, x, will be a1, the derivative of a2, x squared, will be 2a2x, the derivative of a3, x cubed, will be 3a3 x squared, and the derivative of this term over here, the next term, a n plus 1 x to the n plus 1, will be n plus 1 a n plus 1 x to the n. So when you compute the derivative of a Taylor series, all of the coefficients shift over, and you'll have an additional factor of 1, 2, 3, 4, and so on. The second derivative of this function will be 2a2, and then it'll be 3 times 2a3x, and then 4 times 3a4x squared, and so on, all the way down to n plus 2, n plus 1, a n plus 2, x to the n, and so on. Now what happens is that we have, instead of having just 1, 2, 3, 4, we have 1 times 2, 3 times 2, 4 times 3, and 2 consecutive integers multiplying. Now the equation, our differential equation, tells us that y double prime is equal to negative y, meaning that the negative of this first line over here will be equal to the second line. What does that tell us? That tells us that this constant term must be this constant term. So 2a2 is negative a0. It tells us that this x term is this x term, so 3 times 2a3 is equal to negative a1. The quadratic term will tell me that 4 times 3a4 is negative a2. The cubic term will tell me that 5 times 4a5 is equal to negative a3. And if we look down further, the next term over here will tell me that 6 times 5a6 is equal to negative a4. And the next term over here will tell me that 7 times 6a7 is equal to negative a5. And we can find a pattern from this. The pattern from this is that 2n times 2n minus 1, a2n, is equal to negative a2n minus 2. And the pattern over here will tell us that 2n plus 1 times 2n, a2n plus 1 is negative a2n minus 1. So, if we know a0, we know a2. If we know a2, we know a4. If we know a4, we know a6. If we know a6, we know a8, and so on. So if we know a0, we know all the even terms. If we know a1, we know a3. If we know a3, we know a5. If we know a5, we know a7. So if we know a1, we know all the odd terms. So what we'll do is we'll take our original series and we're going to split it into two parts. Our original series will be the sum, n goes from 0 to infinity, of a2n x to the 2n, plus the sum, n goes from 0 to infinity, of a 2n plus 1 x to the 2n plus 1. And now I'd like to write a 2n and a 2n plus 1 in terms of a0 and a1. So we can achieve that by doing the following. If we look at this first column over here, what we'll do is we're going to multiply all left-hand sides, and that will be equal to what we get if we multiply all right-hand sides. If we multiply all the left-hand sides, we will have 2 times 3 times 4 times 5 times 6 times all the way up to 2n. So we'll have 1 times 2 times 3 times 4 all the way up to 2n. And we'll have a2, a4, all the way up to a2n. If we multiply all the right-hand sides, we will have a whole bunch of negatives. We'll have negative 1 to the n. We'll have a0, a2, all the way up to a2n minus 2. And now we can observe that all of these will cancel out, except the a to the 2n and the a0. So all that remains is the a0 and the a to the 2n. And what we have here is we have that a2n is equal to negative 1 to the n a0 over 2n factorial. By a similar argument, we can see that a2n plus 1 is negative 1 to the n a1 over 2n plus 1 factorial by the exact same reasoning, which tells us the solution of our equation, y is equal to the sum, n goes from 0 to infinity, of negative 1 to the n x to the 2n over 2n factorial, plus, and of course these terms are all going to have an a0 in front of them, so a0 comes outside, plus a1, the sum, n goes from 0 to infinity, of negative 1 to the n x to the 2n plus 1 over 2n plus 1 factorial. And we recognize from Calc 2 what these expressions are. This first expression over here is a0 cosine x, and the second expression over here is a1 sine x. So the solution to this equation, y double prime plus y equals 0, is a constant times cosine of x plus a constant times sine of x, and we can verify that's true simply by plugging it in and checking. Furthermore, we know that sine and cosine are linearly independent, so we found a general solution to this ODE using the Taylor series method. Thank you very much.